Herein we'll be talking about alcohols. In this lecture, you will realize that the alcohols are compounds in which a hydrogen in water is replaced by an alkyl group. If you note, the structure consists of an oxygen that is sp3 hybridized, so it's just slightly away from the idealized 109.5 of sp3 species. And if you look at the electrostatic model, it's that the oxygen, the region where the oxygen is quite red, meaning it's quite basic. And the region where the hydrogen is quite blue, so it's quite acidic. This is terribly important later. We'll cover the nomenclature of these alcohols, the structure and physical properties of these alcohols, including hydrogen bonding that affects both the boiling and melting points. And then we'll review the synthesis of alcohols via alkenes, and we'll come across a novel approach to the synthesis of alcohol via the reduction of carbonyls. We will then probe reactions of the alcohols. As far as nomenclature is concerned, then we always end with the suffix OL, O. And most of the rules that apply to alkenes and alkyl halides also apply to alcohols, where we commit to the longest carbon chain, but it is that which contains alcohols, because the OH has preference over halogens. For example, you can see here we have this compound, and first glance we have an octane system or octyl system. But because the chain is that we're going to, as primary, is the species with the alcohol, then it is the 6-carbon chain. And the 6-carbon chain starts with 1 at the carbon that is attached to the OH. So therefore, you can see that we have an hexanol, and that hexanol has a propyl group attached to it. The propyl group is attached at carbon 2, hence 2-propyl 1-hexanol. We can look at rings. Again, with rings, the alcohol here is directly attached to the ring, so it is a cyclohexanol. And you can see that there's a methyl on 2 and a methyl on 3, hence the 2,3-dimethylhexanol, cyclohexanol. Note, for this compound, you can see we have a 5-carbon system, so it's a pentanol. Alcohol takes precedent, and so it's going to be 2-pentanol with the bromo on 3. As stated, alcohols have a hydroxyl group bonded to carbon, and we can therefore distinguish 3 types. There is the primary alcohols, there's secondary alcohols, and tertiary alcohols. Note that due to the presence of the hydrogen bonding, then alcohols have much higher boiling points than ethers, the ethers and alkanes or alkyl halides. For example, you can see here, this ethanol has a boiling point of 78 degrees. Compared to an ether of similar molecular mass, the boiling point has dropped dramatically. With alkane, it's even more drastic because this does not have a permanent dipole. We can also see normal trends for organic compounds where there is an increase in boiling point as we increase molecules. Herein we have the alcohol act as an acid to generate an alkoxide. So in the case of ethanol, we deprotonate to form the ethoxide. And herein it acts as a base. We can see there's a proton right here on this carbon that's been deprotonated by water acting as a base to give you an alkene in this case. We can probe the acidity of alcohols in compare under containing species, such as the alkynes and the amines. Note that this is the series where we can see there's increased acidity moving from right to left because it's based on the stability of the conjugate base. This is a very powerful base. It is a carbon anion, negative charges on carbon, so there's no way to stabilize it. So it's powerful base. So it's very unstable, meaning that this is a very weak acid. On the other hand, both the hydroxide and the alkoxide has the negative charge on oxygen. Guys, if the negative charge is on oxygen, the oxygen can stabilize its negative charge. So these are more stable conjugates, hence they belong to stronger acids. This information to generate bases that can be used to protonate alcohols. Chief amongst these are sodium hydride, the amides, and the alkali metals themselves. The Grignards are rarely used. But you can see that in all cases, we generate the oxide and gaseous molecules. So very efficient reactions. Note that as we move down this group, then there's an increase in acidity. And the question is why? Well, let's look closer at the butanol and compare it to, say, for example, ethanol. And you'll note that with butanol, yeah, molecule, and this is wrongly labeled, by the way, but with butanol, we have a large species. So this is tert-butanol. This is a tert-butoxide. So this is supposed to be here. And this species cannot be readily solvated. Because of that, it's less stable than the methoxide. So therefore, the methoxide being readily solvated becomes more stable and hence a more stable base, a stronger acid. Hence, in this case here, we have ethanol being more solvated, the alkoxide being more stable, yet is the acid for a more stable conjugate base. If we look at this ethanol compared to the ethanol where we have trifluoromethyl, so it's trifluoroethanol, you will note that this is a much stronger acid. The reason for the stronger acidity of the trifluoromethyl, trifluoroethanol, is that the species has tremendous electron withdrawing ability, this fluorine, and so it stabilizes the alkoxide. Stabilize the alkoxide. So hence, if you stabilize the alkoxide, stabilize the negative charge, then that relates to a stronger acid. Hence, you can see the difference in those values. When we compare straight acyclic system, for example, this ethanol, and you compare it to the phenol, you can see the phenol is a much stronger acid than the ethanol. And the reason for this is that the phenol, once deprotonated, gives you the phenoxide, which is stabilized by resonance. The lone pair on this oxygen that results, this negative charge that results when we deprotonate, sits solely on that oxygen, so it's not very stable. We can also look at phenols when we add different groups onto the ring. And note, if we have an electron withdrawing species, like this nitro, for example, on the ring, then we increase the acidity because we are stabilizing the resulting phenoxide. If we have more than one group, withdrawing group, then you can see that our acidity increases dramatically. And now we will review the synthesis of alcohols. And the new material will cover reduction of carbonyls using lithium aluminum hydride and reactions of carbon and ions in the guise of Grignard's and lithiated reagents. In our review, remind ourselves that we have the acid catalyzed addition of water to this asymmetric alkene to realize a carbocation, which is on the most substituted carbon. Hence, the final product is an alcohol where the OH is on the most substituted carbon. The same thing can be achieved with the mercurium acetate, but this is a two-part reaction. So we use the sodium borohydride to cleave this residue. And we realize also another Markovnikov type reaction. The difference between the two, however, is that in the acid catalyzed addition of water, it is quite harsh, and rearrangements, if possible, will happen. On the other hand, the mercurium is a bit toxic, but it's mild, and no rearrangement will occur. We can also achieve the anti-markovnikov addition of water by using borane in the presence of basic peroxide. And herein you can see that the OH is on the least substituted carbon. We can produce diols, so the syndiol using osmium tet, or transdiols by epoxidation followed by attack. In this case here, we're attacking with water. So we insert oxygen in the double bond and then add the water add one OH trans to the other OH by adding water. We can ask ourselves this simple question, and you should pause right here. And we realize that addition of water using an acid as a catalyst would give you the Markovnikov product, i.e. the OH will be on the more substituted carbon. And so we found out that these two fellas here will be our answer, because remember that we get a carbocation planar sp2, and we can attack above and below this plane to give us a racemic product, hence C. And you can review this in the past lecture titled Alkene Chemistry. Herein, you can see that we've used osmium tet peroxide, and this will give you a cis diol. So that's the end of that review that we should have done earlier with alkene chemistry. And now we can move on to synthesis of alcohols using carbonyls. So we're reducing carbonyls. And if you note here, yeah, we have two major reagents. We have sodium borohydride, which is milder than and very strong. So here we can achieve the reduction of an aldehyde using sodium borohydride to give us a primary alcohol because we've added dihydrogen across this double bond. The same thing occurs here with a ketone. We end up with a secondary alcohol. We've added dihydrogen across this double bond. Lithium aluminum hydride will achieve the same results as the sodium borohydride. But unlike sodium borohydride, lithium aluminum hydride react with acids and esters. So herein, lithium aluminum hydride can convert an acid to a primary alcohol, and an ester can also be reduced by lithium aluminum hydride to a primary alcohol. We can then talk about Grignard reagents, and this is terribly important to us because that's in organic synthesis. And we start off with a alkyl halide. This alkyl halide will react under anaerobic conditions with magnesium to give us the Grignard reagent. Look carefully because the Grignard reagent has a carbon anion, which is, of course, unstabilized, and therefore it serves as a very powerful nucleophile. Difference in the electronegativity between the carbon and the metal, 2.5 to 1.3, is great enough to generate this strong nucleophile. The organolithiates does the same job as the Grignards. So we can look at an example here, for example, of the Grignard attacking a carbonyl, in this case an aldehyde, to give us a secondary alcohol. It's a two-step mechanism because we attack this electrophilic center, end up with an alkoxide intermediate, which we then quench to give us the alcohol. Here we have a ketone, so we realize a tertiary alcohol. And here we have an ester, which gives us a tertiary alcohol. The mechanism of this we will focus on in second semester organic chemistry. The limitations for the Grignard is quite simple. You cannot have any acidic protons around because your Grignard will die on these acidic protons. So if you're using some sort of alkyl halide to form a Grignard, once you have this type of system present, then of course your Grignard is destroyed to become an alkane. Similar, if we have any other electrophilic centers around, such as these electrophilic multiple bonded species here, then of course they will compete with your substrate. So you do not want any electrophilic multiple bonds around. Simple question like this could be asked. And if you notice carefully, we have a Grignard reagent and we have formaldehyde followed by a quench. So we know that we're forming an alcohol. So there's a coupling between this carbon and this carbon. And so we now have a 3-carbon system. So that leaves out C and D we can eliminate. But B is an ethyl. So our result, therefore, is this. So we start off with this ethyl system, add a carbon, and now we have the propanol. So that was a brief coverage of the synthesis of alcohols. Now we will look at the reaction of alcohols. And we'll mainly cover the fact that the oxygen atom of the OH can be nucleophilic and it is weakly basic. And the hydrogen atom, of course, we saw earlier, is quite acidic. Now, the OH group cannot act directly as a leaving group. And so to allow for substitution, we usually convert it to an alkyl halide or some salt species like a tosylate. But we can forward to substitution and elimination reactions in alcohol. And then we can talk about oxidation to form carbonyls, which is the reverse of the reduction of carbonyls to form alcohols. So as a reminder, this OH cannot spontaneously dissociate to give you a carbocation in a unimolecular mechanism because this is too strong a base, the OH minus. We cannot attack directly the backside of a carbon either with the OH present because, again, that's a very, very poor leaving group. So no reaction will occur in these cases. However, if we convert to an alkyl halide, then alkyl halides, as we've seen, make very good leaving groups. And so, therefore, we can use them. We can use phosphorus tribromide or phenyl chloride, all to achieve the production of alkyl halides, which chemistry is separate from this. We can always cover that. And if you look at the next line, you will find these available to you as well. So the reactivity of these alcohols with the mineral acid is much faster than the primary because it occurs via a carbocation. The mechanism, of course, is taking advantage of the basic oxygen, attacking a proton in the mineral acid to give you this intermediate, which has this leaving group, which you recognize as water. So if you look at this reaction, for example, where we have butanol with HCl, the substitution reaction starts with the first step where we protonate the OH. The intermediate that follows is then species that undergoes dissociation of water to give us a carbocation. The resulting carbocation is electrophilic in nature, so it will get attacked by the chloride to give us our product. Primary alcohols and methanol, of course, they react to form alkyl halides under an SN2 mechanism. So it's quite simple. Yeah, once we protonate, we can have a backside attack, yeah, to realize our product. Take a shot at this question. Exactly. The product that results is substitution, but of course, because we've gone via the intermediate, which is cationic and planar, we can adopt resulting in a racemic species, i.e., both isomers. Phenyl chloride and phosphorus tribromide can convert primary and secondary alcohols to alkyl chlorides and bromides, respectively, without rearrangement. And so, therefore, it becomes quite efficient for us because we want to avoid any type of rearrangement, this is a very nice way to go. It is an SN2 mechanism, so you'd expect reversal of the stereogenic center if there is one present on that carbon with your alcohol. Question like this is to familiarize yourself with the reagent, phosphorus tribromide. Remind yourself that this will convert the OH to a, so therefore your answer should be C. We can talk about the tosylates. The tosylates and the mesotolates, they're very good leaving groups. Not only are they good leaving groups, but we also use them as protecting groups. Now, protection we'll talk about in a later lecture. But look closely because tosylate is quite a large molecule and we react it with the OH. So there's a simple substitution reaction occurs. And this is the tosylate derivative. This carbon now becomes a rather good electrophilic center because this is quite a good leaving group. Note that when we do react with tosylate, we retain the stereogenic center, but when the substitution does occur, it occurs via SN2, and so there is inversion of that configuration. Answer this question for us. Note that it's a direct conversion of the OH to the tosylate. With that, we can now talk about the elimination of water, i.e. dehydration reactions to form alkenes. Herein, sulfuric acid will act as a catalyst and reaction except for primary alcohols. And in this case, it's not very efficient because rearrangement, if possible, will occur. So we usually tend to use phosphorus oxytrichloride, and herein we have an E2 mechanism because there's no rearrangement that will occur, especially when we're using primary alcohols that can rearrange. You see this example here where we have this cyclohexanol and the OH is protonated, catalyst, so it's protonated to form this group. Once this water leaves, then it can act as a base and attack our proton. Loss of water, of course, realizes the carbocation, so this is the rate determining step. Deprotonation here realizes your Zaitsev product. Because this is an E1 mechanism, then of course, as we stated before, you'd expect that the rate of substitution will, rate of elimination will occur the following order because these are the stabilities of the carbocation, where this tertiary is much more stable, therefore low activation energy than the primary. As we stated before, there is a propensity for rearrangement to occur if it can occur. And so in this example, you can see that we have the production of a secondary carbocation, but instead of elimination followed this directly, we have a 1,2 hydride shift to give us the more stable tertiary carbocation. And so when we do have elimination, we end up with this alkene instead of an alkene here substituted, or the Zaitsev here, which we tri-substituted. With primary alcohols, we can go via the E2 pathway with the phosphorus acid. And with that, we can answer a question like this. What is the product, major product of this secondary alcohol with sulfuric acid in the presence of the sulfate anion, the hydrogen sulfate anion is a very poor nucleophile, and so the elimination reaction will dominate. It should be B. Talked about the advantage of using the phosphorus octrichloride, and here you can see octrichloride in the presence of pyridine. The reaction is an E2 mechanism. Possibility of rearrangement occurring is reduced. With that, we can now talk about the oxidation of alcohols. Note that we can start off with a primary alcohol and remove dihydrogen. And if we remove dihydrogen, we end up with an aldehyde. We can further insert an oxygen to form a carboxylic acid. Of this process is, of course, reduction, which we've covered already. We can also insert oxygen into a ketone to form an ester, which is not shown here, but this we'll talk about in organic 2, i.e. second semester organic chemistry. Tertiary alcohol oxidation is not possible, so we're just focused on this area here. Note, we got to distinguish again between a primary, secondary, and tertiary alcohol, and realize that oxidation is only possible for primary and secondary alcohols, respectively, to form aldehydes and ketones. And further oxidation can occur with aldehydes to form acids. The reagents that we use typically are chromic acid or sodium chromate, which is harsh, and pyridinium chlorochromate. This is PCC, and this is a very mild reactant. You can see the structures here. Realize this, that again, these can be used for oxidation of primary and secondary alcohols. In case of PCC, which is quite selective, it is a mild oxidant and can be stopped at the aldehydic level. Chromic acid, however, is harsh. So even though both PCC and chromic acid will convert a secondary alcohol to a ketone, chromic acid with a primary alcohol will not realize an aldehyde as the end product. In fact, the oxygen insertion will take place, i.e. maximum oxidation will take place to form the acid. A question like this, where we have a primary alcohol being converted to an acid, should be recognized immediately as an oxidation. Sodium borohydride is a reducing agent. PCC is mild and will only drive it to the aldehyde. MCPBA is oxygen insertion. That's not going to work here. And ozone be used for cleavage. And of course, again, that's not going to work here. And so our answer, therefore, is the sodium dichromate, which is the sodium salt of our. We've finished this lecture, and the next lecture we'll talk about is the ethers. And please do leave comments in the comment section below, and please like and subscribe.